Okay, so this week we have 5 problems as usual. First 2 problems are more of warm-up problems, and then the last 3 are focused on dynamic programming. And now that we have further into the term, I'm not going to spend so much time showing you all the code. I will still pop the code on screen, and you can pause the video if you want to take a look at the code. But otherwise, I'll just be talking about the algorithm itself. So let's see. First problem, you have this person that wants to do yoga for n days. Every day you have AI, which is the amount of time that this person can spend on that day at most, but he's allowed to leave earlier than that. He wants to spend the maximum amount of time possible over the n days, but every day must be at least as long as the previous day. So that is to say, the amount of time he spends on yoga over the days is non-decreasing. Okay, so what's the input like? You have up to 300,000 number of days, and there are n integers. Each number, it's at most 10 to the 4. Okay, so you have n, which is at most 3 times 10 to the 5, and then AI is at most 10 to the 4. Okay, so now what we have to worry about is if every day you spend exactly that much, that's 3 times 10 to the 9 total. And that, it's bigger than 2 to the 31 minus 1, because 2 to the 31 minus 1 is roughly 2.147 times 10 to the 9. So what is 2 to the 31 minus 1? That's the maximum normal 32-bit integers. Okay, so right off the bat, before we even figure out how to do this, we have to be careful that the total answer could possibly be bigger than a 32-bit integer. Okay, so you can either use an unsigned integer, which allows you to go up to 2 to the 32 minus 1. So if you use unsigned, and that would be good enough because it's about 4 billion, or you can just use int64. Okay, 64-bit is definitely way bigger. Okay, so now let's look at the problem again. So you have A1, A2, up to AN. These are the amount of minutes of whatever time unit they have that you can spend per day at most. So whatever you actually spend, let's call it S1, S2, and so on, whatever you choose to spend must be no bigger than whatever they give you, but also in this sequence, you have to choose something that's non-decreasing. Okay? So you want to spend as much time as possible total. What is the best way? Right? So you want to spend, for example, the first day as much as possible, but if you spend too much time, maybe you won't be able to spend. So, for example, if this is 10 and this is 5, right? You like just look at the first day and say, well, I want to spend 10 minutes or 10 unit, but then the next day you realize, oh, you can't do that because the next one is 5. If you're moving in from left to right, you will always have a little bit of difficulty trying to figure out what I can spend next time because I don't know what I can do because this 5, right? Just because A2 is 5 doesn't mean you can first spend 5 here because next day maybe it's 3, right? You might be limited. And unless you scan forward far away, you will not be able to tell how far you can go. On the other hand, if you scan from right to left, okay, you look at this here, whatever this is, you can spend as much as you want just the last day. You can spend all of it. Why? Okay, so let's say this is, I don't know, 15. Because at this stage, 15, there's nothing that comes after you. So you're not constrained by what comes after you at all. Right? You can just spend as much as you want. But now, when you look at the previous one, maybe this is, let's say 10, and you say, okay, 10 is lesser than 15, so I can still spend as much as you want. But the next one might be 20, and then you realize, oh, I cannot spend 20. What can I spend? I can spend at most 10. So now I know that I can spend at most 10. And so all you have to do is scan backwards and keeping the minimum you have seen so far. So as you go this way, figure out the minimum, and you can never, the previous one can never be more than that, right? So basically all you have to do is you keep a running minimum. So minimum of a I to n. So at any particular position, let's go at I plus 1. Okay, AI plus 1. So if I'm looking at here, I want a minimum of everything after me. And then what I choose, Si, is simply the minimum of, well, of AI and this. Or in other words, it's just the minimum of AI uh, AI dot n, like this. Okay, I cannot spend any more than that. And this is the maximum I can spend. So basically every day, what I can do is the minimum of everything from that day on. And and if I were to compute it backwards, then every step I don't have to recompute everything. I can just uh, incrementally incorporate the next element into my running minimum. Okay, and that's pretty much all there is to it. Now, if you really, really want, I suppose we talk about things like range maximum or range minimum query. You can use range minimum query to answer this, but it's an overkill because we are asking for different ranges, but in a very organized way. It's always just increasing one more element at the front. So let me just show you quickly. Code. Um, so, um, so I read in the n numbers, and then instead of doing it backwards, I do it forward. But before I do it forward, I do a reverse. So you can write your loop backwards, or if you like, you can write your loop forward. But before you do that, you reverse. And then here I just have a running minimum, which is what I call previous, and I initialize the 10,000, which is the maximum possible. And then basically every time I just incorporate the new minimum, the minimum with incorporate into it with the next element, and then I add up what I can do, and I print out the answer, and remember that it's 64-bit integers. Okay, if you don't use that, you might get a wrong answer. Okay, so that's first one. Second problem. So you have a order problem set. You have n problems. They're all distinct difficulties. And you want to separate into k sections so that the problem P is assigned to this section. Then for every pair of sections I and j, every problem in section I is easier than every problem in section j. K must be greater than 1 and a factor of n. So you want to know, given a set of problems, up to 50 problems, for what k values of k can this be true? And if none of them works, it's minus 1. So basically, because n is so small, you just try all k, right? For all k from 2 to n, if it's not a factor, you don't have to do anything, right? Because it's just, it says that k has to be a factor of n. And then after that, for each k that's a factor, you check. How do you check it? You divide it, for example, if k is 2, you divide in groups of 2, right? So 1, 3, 2, and 4, 5, 6. And you want to make sure that this group, everything is easier than the next group, and so on. Now, the fact is that you know that the numbers 1 through n are going to appear. So there's not any arbitrary numbers, it's 1 through n in some order. So in the case of two groups, for example, 6 divided by 2 is 3. So you know that the first 3, the maximum has to be 3. And then the next group, the maximum has to be 6. And then the next group, the maximum has to be 9 if there are more than 6, and so on. So you could, I guess, do what they say and just say, for everyone here, it's less than the next group, and check that. That's okay because the numbers are so small. But you could also just check the maximum here. It's less than the minimum here. And then for each group, the maximum is less than the minimum of the next group. That's another way. Or you can just say the maximum of the first group better be 3. If it's not 3, then something is wrong. And the maximum next group has to be 6, and so on. There are many ways you can do this. So without showing you too much, saying too much more, I'm just going to show you my code. So you get n, you read in the difficulties, then I have a count of how many k's that works. So for each k from 2 to n, I check if there's a remainder. If there's a remainder, then it's not a factor, so I ignore it. Then I check. So good is a flag that makes sure that it's k is still good. And then what do? I go through the k groups. Okay. Then I figure out the start and end of that chunk. Okay, so when I is 0, then 0 and n over k. Okay, and this is the C++ start and end. So start is inclusive and end is 1 too far. And then I just ask if the maximum element in that group, it's exactly the same as n. So again, if I'm dividing groups of 3, first group, the maximum has to be 3. The second group, the maximum has to be 6, and so on. And this is going to give me a true or false because it's an equals comparison. And then I end it like this. So basically, if any one of these things is false while I'm going through the loop, good will be false because I'm using and. And if all of them are true, then it will stay true. So if it goes to every single group and it's still true, that means I found a k that works. So I print out the k and remember that I have at least one answer, because at the end I need to know if there are no answers, then I need to print -1. Okay, so those are the two warm-up problems. All right, so the point of this week's exercise is about uh, dynamic programming. So dynamic programming, the idea is that you try to solve some problem, and maybe we find a way to do this recursively, and we hopefully realize that even though we're doing this recursively, there are actually not that many different um, inputs that you can put into the recursion. So, but some of the inputs might be asked for many times, like Fibonacci sequence. And so we will try to remember things that we have computed so that we don't have to do it over and over again. So we make sure that every single possible input, if we are ever asked to compute twice or more, it will only be done once. Okay, so let's see here. Tight words, right? You have an alphabet, numbers between 0 up to 0 to 9, but it could be less. A word of length n over this alphabet is tight if any two neighboring digits do not differ by more than 1. So then it says, for example, if k is 2, and you can only use the digits 0, 1, and 2, then the tight words are 0, 0, 0, 1 for length 2 is this. So for example, 0, 2 and 2, 0 are not tight, but everything else is. So there's 7 of them. Okay, and then it says because there are 9 words of length 2, the percentage is 7 over 9, which is this much. Okay, so now they tell you given, okay, two integers k and n is at most 100, k is at most 9 up here. What percentage are tight words? Right, so that's the question. All right, so how do we approach this? Right, what does a tight word look like? So you have n characters, so you have a0, a1, a2, an minus 1. Let's do it like this, right? Now, how do we do this? How we would to break this problem apart, right? So if you were not just doing it, I don't know, trying all possible ways, you would maybe try every single numbers, single digits 0, 1, 2, up to k, and try them all, right? Try them all. And now, once you decide that you want to try a0 is 0, a0 is 1, and so on, you then recurse and try to find how many tight words there are, right, on recursively. However, when you know that you have picked A0, now you can't just pick any A1s you want, right? If you pick 2, then A1 has to be either 1, 2, or 3, because anything else would be too far away. Okay, so your recursion, once you decide what A0 is, you would want to recurse and say what is recursively. So I'll just say use the word f to say how many or proportion or whatever you want. How many there are. Let's just say that I count. Instead of doing proportion, I count for now. Well, how many are there? Well, I have 2 parameters now. Why do I have 2 parameters? Because I have to say how many, what is the length I still want, but also what is the starting digit. Fn minus 1, 2 plus Fn minus 1, 3. And this is, what is this? This is F of n comma 2. So if you know that you want to start with a 2, then recursively, it's once you chose a 2, then it's the number of length n minus 1 things that starts with a 1, starts with a 2, and starts with a 3. Right? So generally, you have 3 terms. Now, of course, if you start with a 0, so n0, well, you can't start with -1, so you can only start with 0 and 1. Right? Assuming that k is at least 1. And here, of course, if k is less than 3, then you have to chop off this term. If k is 2, then you have to chop off this term, for example. Okay? Now, the point is that this first parameter can be between 0 to 100. And here is between 0 to k, which is at most 9. So there are only there are only 101 choices here. There are only at most 10 choices here. So altogether, there are only at most 10 times 100. Let's just call it 1,000 different input that you can ask. So basically what you do is you have a table that say, well, uh, here's the answer if somebody ever asks me what is f of n and start. And the first thing I do is I ask, have I seen this before? So maybe at the beginning you initialize everything to -1. So you know that you haven't seen it before if you have seen -1. And if it's not -1, you just return it. You don't do any more calculations. But if it's -1, then you do this calculation recursively. And then before you return the answer, you also store the answer in the table. And that's basically all you have to do. Now, one thing though, this is the way that I wrote it is a count. How many there are. You're looking for probability. So the total number, it's always k to the n. So you need to divide the total by k to the n. But these numbers are really big, right? K is at most 10, n is at most 100. You can't actually possibly use a number like this as an integer. So instead of counting, what are we going to do? We are actually going to just compute a probability. So we use the doubles. And here, if f of n over 2, n comma 2, what's the probability that what's the probability for things starting at this? Well, it has to be the sum of these probabilities, right? But then you can divide by k as well, because you add another digit, okay? So something like this as floating point numbers. Sorry, it's not k, it's k plus 1, because it's 0 to k, so when k is 9, for example, then they're 10. So this is actually k plus 1. Okay, and also, of course, what is the base case, right? So if you have empty string, or maybe actually, maybe in this case it's easier, f of 1 something. So if you have length 1, right? So if you have length 1 and you start anything, doesn't matter what you want to start, let's say start at 1, what's the probability that is a tight word? It's 1 over k plus 1. Okay. So that's basically it. Okay, so just quickly show you the code. I read in k, I read in n, and then the max digit is k. So I have this table that I set to -1. So -1, this table is doubles, okay? Percentage of tight words of length n ending with the I did ending with the digit k instead of starting, but it really is the same thing whether you look at it forward or backwards. And then the answer, well, if I know how to compute the number of tight words, f of n, j, n is the length and j is the ending digit or starting digit, well, then I have to try all the possible digits, and I add them all up, and that's my probability. So how do I compute f of nj or nk? First thing I check, if I've seen this in my table and it's not -1, if it's at least 0, then I just return it. I don't do anything. If it's exactly length 1, then for sure it's tight. So I just take the probability. It's just this divided by that. Okay, so I use 100 because it's asking for percentage instead of probability. So that's why I use 100 instead. Otherwise, I set this to be 0 and then I just do that sum, right? And here I do go from k minus 1 to k plus 1 because those are 3 digits, but in case k minus 1 is 0, the max will take care of it and don't go negative. And in case k plus 1 is too big, then I also won't go over. And that's it. Okay, so the coding is relatively straightforward, but it's how you model this and then figure out how to deal with this. So a lot of times when it comes to combinatorial things, like when you're counting how many type of objects fit a certain pattern, it's quite often the case that you want to do things recursively by thinking about how to chop off the first one or the last one and then recurse, and then hopefully you'll recognize that the recurrence relation doesn't have that many different input parameters, and then you can use dynamic programming. Okay, next one, permutation descent counts. So you have a permutation of 1 to n, and you want to know how many permutations there are that have a certain number of descents. So for example, if you have 3 of them and 1 descent, what is a descent? Descent is a consecutive pair that is out of order, right? So 1, 3, 2, that's a consecutive pair that's out of order. 2, 1, 3, 2, 1 is a pair. 2, 3, 1 here, and 1, 3, 1, 2. So if you ask how many permutations of 3 objects have 1 descent, then the answer is 4. And then to avoid the answers being very big, compute your answers modulo this thing. Okay, and it says they have up to 1,000 data sets, and the numbers are n is at most 100. So right away, you cannot possibly process 100 factorial permutations. You can't just try them all. Okay, so you have to do something a little bit smarter. All right, so let's think about this. So PDC, which is the name of the thing, and K is the number of permutations with K descents. Okay. What are some easy cases? Well, if the number of descents is 0, it's always 1. Why? Because if you don't have any places that are out of order, then the permutation must be like 1, 2, 3, 4, up to n. If you have exactly n minus 1 descent, that's also 1 because the only permutation that has that property is the one that's completely backwards. So every pair is a descent. Okay, so those are the simpler cases. Well, what if you have something like, I don't know, something small? If you only have one thing, well, if you only have one thing, then that's it. Anything else? I'll just put anything else. It's 0 if this is bigger than 0, right? If you have only one thing that you can permute, there cannot be any descent. Okay, those are kind of simple stuff. Now also, they tell you that this is at most 100. Oops, not 1,100. And this is at most n minus 1. So you know that this cannot be more than 100 square different possible inputs, right? Because there's at most 100 here, and there's at most 100 here. So altogether, there's at most 100 square. All right. So let's think about a permutation, right? I don't know, 4, 1, 3, 2, and put a 5 here. Okay, so this is a permutation with 5 objects. And there are how many? 1, 2, 3 descents. Okay, now let's think about what we can do if we want to have 6 objects. So why am I thinking about this? Because as I said, with combinatorial things like permutation combinations of different properties, I want to know if I have something a little bit smaller, can I build it bigger, or recursively, if I have something bigger, can I reduce the problem to something smaller? Okay, so now where can I put this 6? I can put it here, 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 or here, right? If I were to insert a 6 into this permutation that I already have, this has right now 3 descents. What is going to happen when I add the 6? Well, if I add a 6 in the beginning, I will have one more descent. If I add a 6 in between 5 and 4, I don't actually change anything, because I would then have a descent between 6 and 4, but there won't be a descent between 5 and 6. Okay, so I still have 3 descents. When I put a 6 between 4 and 1, I get the same idea. But when I put a 6 between 1 and 3, I get an additional descent. And when I put 6 in between 3 and 2, I don't introduce anything. And I put a 6 in the back, I also don't introduce any descent when I put the biggest number. Okay, so what just happened here? When I take a permutation of 5 things, and I have 3 descents, if I add the biggest number between the descents that I already have, I don't change anything. Or if I put it at the end, I also don't change anything. So what does that mean? For any, if I want to get, let's say, n equals to 6, and I want k, which in this case is 3 descents, then PDC of 6, 3, I can take every one of 5 objects with 3 descents, and I can insert 6 in 4 possible ways. Why 4? This in between each of the 3 descents, and also at the very end. And still have exactly the same number of descents. That's one possibility. Or, what else can I do? I can take something that have 2 descents. So 2 descents, so for example, 5, 4, 1, 2, 3. So this is something that have 2 descents. And I can put 6 where? I can put 6. So if I have 2 descents, I want to introduce another one. I can put a 6 here. I cannot put the 6 between the 2 descents, but I can put a 6 here or here. So there's 3, every time I see something with 2 descents, I can put a 6 in 3 different ways to get something with 6 elements and 3 descents. And this it's more or less the recursion. Okay, so of course I'm using specific numbers 6 and 3, but we can generalize with the same argument. So what is the same argument? That I can do n minus 1 k. So this is one fewer element with the same number of descents, and I can put them in k plus 1 spot. K plus 1, why? Because you can put it in between any of the k descents and not introduce a new descent, or you can put it at the end. Or you take something with one fewer descent, and now how many places can you put it? Well, you can count, or you can do a different, but anyway, you can say that basically how many spots are there, right? If you have n minus 1 things, so in this case 5, there are 6 spots you can put things in, right? 1, 2, 3, 4, 5, 6. Before and in between and after. So there are n spots that you can put things in. But this many are no good. Why no good? Because these are the places that are in between the descent and at the end. Just use the same argument as we did before, right? K plus 1, we used k plus 1 before. Now it's k minus 1 plus 1. And if you simplify that, this plus 1 and minus 1 goes away. And this is just simplified to n minus k. And that's it. Okay, so you have the recurrence here. Right? We have the base cases here, right? So these are base cases, I guess. And that's it. Okay, what did this say? Permutation descent. Okay, so again, I set everything to be -1 at the beginning, just to say that it has not been done. And here we are. Right, so I have a mod, which is the number that they tell me. I have a table, and then at the beginning, a base case. If I ever ask v is less than 0, then it's 0. And if it's n is equals to 1, then v better be 0. Okay, otherwise, I check if I've seen this before. So this is a little trick, I guess. Instead of typing this thing all the time, I use a reference variable, and you may probably just think of reference as pass by reference, but you can declare reference variables just the same. And then this, from now on, this word answer is just an alias for this table entry, so I don't have to type this all the time. If it is already bigger than or equal to 0, then I just return it because I've computed before. Otherwise, I set it to 0 and I just do these two things. The only thing that you have to be careful about is you have to reduce by mod every step carefully. Okay, so this is, this part and then mod. Then I add it, but add the mod parts, and then at the end I mod it again. Okay, so I don't get too big. So the computation itself, it's, I guess, not that difficult once you figure out the actual formula, right? But it does take a bit of thinking to get this formula out. Okay, last one, word clouds. So you have these boxes, basically. If you read the problem, you basically have a bunch of boxes, and this sheet of paper has a maximum width. You are allowed to put things into lines. So for example, here, you put the first 3 boxes on the same line, and then you can't fit the next one. So the next one have to start the next line and so on. And these boxes have to come in sequence. So this one has to be before this one and so on. And if you go from left to right, um, and then up and down, they must come in the same sequence. You can keep things on the same row as long as it does the total width of that line hasn't exceeded the width of the paper, but you can break earlier. And this line, right, this line has three things, and the height of the line is limited by the maximum height of the three things on that line. And your goal is to minimize the total height. And they said, okay, this one is it's one way, and then if you do the same thing, and you instead of keeping this last one in the first row, you break it and go down like this, and it turns out that the total height is actually smaller. And so you want to, given a list of these words at the maximum and the specific maximum width of the big box, build a word cloud with the minimum height. Okay, and you ask what is the minimum height? Okay, so there are up to 5,000 words, and the width is up to 1,000. There are n additional lines each specifying the bounding box of one entry in the order in which these entries must be laid out in the cloud. Line describing an entry contains integers w and h, specifying the respective width and height, such that the width and the height are at least 10, at most 150, and then you're supposed to figure out the height. Okay, so I have a bunch of boxes, right, of different width and height, and so on, and then one big box. Okay, I want to minimize the total height. Now, if I only have, actually, I'm going to pause this. Get a drink of water here. How do I pause this? Okay, so let me get back to here. Okay, so if I only have one box, then there's not much I can do. I just have to put it on one line. That's it. But what I can do if it was more, is I can try to say, well, what if, okay, so let's say instead of fitting the first box, what about the last word? So if I only have one word, then of course there's nothing I can do. But I can say, well, what if I try to fit the last two words on its own line? Well, in that case, okay, hang on. Sorry, I skip ahead. What if I just put the last word on its own line, right? If that's my decision, then of course it's going to be the last word, the height of the last word. And then I still have to try to figure out how to fit n minus 1 things, right? Or I can say, well, what if I try to fit the last two words? Well, in that case, it'll be minimum, so the maximum of height n minus 2 and n minus 1. I guess I should use brackets like this. And then I have to fit the remaining n minus 2 words. Or maybe I use the last three words in the same line. In that case, it'll be the maximum of height n minus 3 dot dot n minus 1 plus f of n minus 3, and so on. I can maybe try to fit 4 words, 5 words, and so on. So basically, I'm trying to say, well, what is the last line going to look like? The last line must be the last word, last 2 words, 3 words. And I do all of that. And when do I stop? I stop when the width of the last whatever number of words is too much. Right? I know that I cannot fit more than whatever the total is. And then I recursively ask, how do I fit the first whatever number of words? And because there are basically not that many, right? There are only 5,000 words. So f of n, you can ask at most 5,000 different f of n's. Now, how bad is this, right? So how many of these there are? Because every time you compute one of these f of n, it's going to be the minimum. So you're going to compute of all possible choices, you want to compute the minimum possible height, the minimum of all of these things. So if there are this many, whatever that many choices you have, that's called k, then the complexity to compute this, it's 5. It's basically compute each one is, to compute each of these, the complexity is O of k, that most 5,000 things you have to compute. So it's O of 5,000 k. So how big is k, right? So we have to say, well, I guess theoretically, maybe you say, well, I can fit 1 word, 2 words, 3 word, all the way up to n minus 1 word. So it looks like it's up to n. K can be at most as big as n, and then this would be a kind of like an n squared kind of loop. 5,000 square is 25 million. It's not bad, but it's still a lot. But they did tell you that the height, sorry, the width is at most 100. There's at least 10. And the total width is at most 1,000. So that means that you can never fit more than 100 words in, right? Because if you have 100 words in a line, it's at least 1,000 total width. So there's no way you can fit more than 100 words in. So this is actually much less. It's only 100 at most. So 100 times 5,000 is 500,000. That's really nothing. So that's basically it. What is it called again? Word cloud. Okay. So I read in W and H, the width and height and all that stuff. And then I have this table that is just one dimensional. Okay. So if you have no words, then the height is 0. That's easy. Then I use this trick again. And I ask if it's already greater than or equal to 0. Then if so, return it. Because I'm taking the minimum, I initialize it to the maximum possible integers, and then I just walk backwards. Okay, so the maximum height is basically the maximum of the current height of all the words that I've included in this slide. The width is all the words that I've included in this slide. If it's too much, I quit the loop. Otherwise, the answer is the minimum of the original answer more the current height of that line plus the reduction, right? So I goes from n minus 1 all the way down to 0. Okay, and that this would be the recursive part. So again, the code is pretty straightforward to write, but the important thing is, how do we organize this thoughts to break down the problem recursively? So if you have to make, basically you can think of it this way. So in this problem, you have to make a choice, right? You have to make a choice of how many things you, I guess if you work, whether you work forward or backward, let's say you work backwards, You you have to decide when do you start a new line as you go forward or backward. And at every step you have a choice. And so we try all those choices, right? And then we recognize that really there are not that many different things you can ask. So we can just use dynamic programming. Okay, so anyway, those are the 5 problems this week. So I'll stop my video now.